We've been talking about Pascal's law, and Pascal states simply that the pressure of a contained fluid is distributed evenly in that whole contained area. And then we said, why is that? Why is that useful? Well, that's useful because I can put in a little bit of force and I can get a lot of force out if I manipulate the cross-sectional area that it is working across um, to make that pressure. And then the pressure inside is always going to be the same. So that's the pressure of the fluid that's distributing the force from one side to the other side. And then we related that to a piston. So this is a hydraulic cylinder, a piston inside a cylinder. This could be a hydraulic or pneumatic. And we say that the area on one side of this cylinder, this hydraulic cylinder, or sorry, the pressure on one side is the same as the pressure on the other side. So the pressure inside here is the same as the pressure inside here. But the pressure on the first side is acting upon area of the cylinder, this green area here, which is larger than the area of the rod that is acting upon on this side. So here's the cylinder and here's the rod, and the area of the cylinder is higher than the area where the rod's coming out because the rod's taking up space. So we're actually going to get more force on this piston side than the area side. But why? So we want to look at, why does this actually happen? And is this sort of like magic? Is this sort of too good to be true? Why does this happen? So again, let's review our equations. And I'm going to just simplify our simple hydraulic press even further here. And I'm going to say that if I am acting in with a force here, F in, then it's going to act upon a cross-sectional area, A in, to make a pressure, P in, which will be the same as the pressure throughout, that is just called P, which will be the same as the pressure P out. So P in equals P, which equals P out. That's what Pascal said. This is literally what Pascal said. The pressure is the same everywhere. So then the pressure acting upon a cylinder on the way out, then, A out, is going to have a larger force because it's acting across a larger cross-sectional area, A out. So F out is going to be greater than F in. So we're sort of exploiting Pascal's law here. So are we getting something for nothing? No, because of, why does this hold true? Because of conservation of energy. This holds true because of conservation of energy. That's why we can do this, because conservation of energy holds true. So let's explore this relationship in terms of conservation of energy. Something else must be at play here. So if we call, we're going to now call F in, we can call that F1, and we can call F out F2, and A1 is, sorry, A in is A1, A out is A2. P will be the same anywhere. So by Pascal's law, P1 must equal P2, which means that F1 over A1, right? F1 over A1, I could just write it like this, is the same as F over A at location 2. If I want to label these location 1, location 2. Force over area is the same ratio. So F1 over A1 equals F2 over A2. And if I want to just swap these to look at the ratio of F1 over F2, then I would bring the F to the other side and I would bring the A to the other side. And it's a simple math to show that written in this way, I can write this as a ratio of two things. So what this now is a force ratio. The force ratio of, oops. This would actually be, I think I rearranged this a little bit wrong. Hang on a second. I'm going to take these subscripts away. And what I'm going to do is, if I have F1 and yes, I would have F2 over F1. I just want to arrange it this way. F2 over F1 is equal to A2 over A1. Or F1 over F2 equals I just want this to be a positive ratio. A2 over A1. So it means that we have the second condition on the top for both of them over the first condition on the top. The second condition is larger in this case and smaller in this case. So I just wanted those to be positive force ratios. It doesn't really matter because we're comparing the two. But the force ratio is equal to the piston ratio. Force ratio is simply the force of the output piston over the input piston, and the area ratio is simply the area of the output piston over the input piston. So this, while this is true, and we know this from just P equals force over pressure equals force over area, the relationship we know, it doesn't really show us how conservation of energy holds true. The thing that really that we give up here is not for free here. The fact that we haven't talked about yet is the fact that this piston over here must travel a much bigger distance than this piston's going to travel. So this has to displace a volume, V1, and this has to displace the same volume, V2, where V2 equals V1. But if each of these pistons has to displace the same volume, but one of them has such a big area compared to the other one, then this one must travel farther. Travel farther. So this has an increased stroke, piston stroke, and this one has a small piston stroke. And we call that piston stroke D. So the key here is the distance that those pistons have to travel is different. Which one do you think will travel farther? We think about that conservation of energy. We think about that conservation of energy, and we remember for them to be, for the energy to hold true, the volume of the oil displaced must be the same. So piston 1 with its teeny tiny cross-sectional area must displace a certain amount of volume. Piston 2 with its huge cross-sectional area must displace the same amount of volume, then it must not have to travel very far to do that. V1 has to equal V2. So distance D1 is much greater than distance D2. In order for the conservation of energy to be to hold true. So let's look at displacement by bringing volume into this relationship. If we draw that simple hydraulic press again, we have a small piston at the input. We have a large piston at the output. This small piston has a small cross-sectional area. This large piston has a large cross-sectional area. You can draw the pistons just as like a little block in here. And so this is piston 1 and this is piston 2 as a block with their cross-sectional areas. I'm going to apply a force F1 in, and that is going to make a large force F to or out. It makes a large force because there's a large cross-sectional area. But instead of just talking about area, let's look at the displacement. Let's call this D1, positive displacement D1. I'm going to draw this one in the positive direction as well, D2. If I label D2 like this, it would just simply come out negative, which is fine as well. We just have to know common sense where things are moving. The pressure inside here is going to be equal to the force over area of either of these. It'll be F1 over A1, or it'll be F2 over A2. We'll use whichever ones we have values for. But of course, that's called P, and P is the same here as it is here, and it's going to act upon these cross-sectional areas. But if we look in general at what is the equation for conservation of, if we look at conservation of volume, then that means if we look at conservation of volume, that means that volume of 1 equals volume of 2. Conservation of volume of displaced fluid. Okay, so we're going to displace this fluid by pushing down this piston down this much into D1, and we're going to displace this volume by pushing up this piston. And so this is volume 1 displaced, and this is volume 2 displaced, which I drew smaller because I'm pretty sure it's not going to go as far. So if V1 equals V2, but volume is area times distance, in this case, D, displacement. Volume is area times displacement. So then volume has to be area. V1 would be area 1. It's the area of this piston times displacement 1. It's this displacement area arrow equals A2 times D2. A2 times this is D2. If I rearrange these ones, I can see that A1 over A2 is equal to D over D, but it's D2 over A1. So we see that these are not, see, this is, we have to be sure that we look at this relationship properly. This is the small area is on the top here. So it's area 1 on the top. Displacement 1 is on the denominator over here. So it acts in the opposite direction. And A2 is, the bigger area is down here, but the bigger area is on the numerator here. So this here is called the piston ratio. Same piston ratio we had above. Piston ratio. That's the ratio of the areas. Same piston ratio that we have above. And this is called the stroke ratio. Because the distance that a piston travels inside its cylinder has a specific name, a technical name, and that technical name is called the stroke. So what we observe here, we observe smaller cross-sectional area pistons must travel larger stroke. That's what we've shown here. So if we combine those relationships, because we have a piston ratio here, we have a stroke ratio here, and above we had a force ratio. So if we combine all of those then, let's combine all of those. Then what we're going to get is the force out over the force in is going to be the same as the area out over the area in, because um, force out in this case larger corresponds exactly to the larger piston, but it's going to travel less of a distance. Traveling less of a distance isn't necessarily a good thing. It does not do a lot of work. Whereas this tiny piston in the beginning or at the front, or the start that we put our force into travels farther, which, if you're looking at linear motion, it actually does more work. And we can rearrange this, and we can now relate F to D. And it's a simple mathematical matter to observe that F1D1 is equal to F2D2. And these should really ring a bell. We should say F times D, force times displacement. Well, force times displacement, force times distance equals work. Force times distance equals work is something we remember. And work is a type of energy. An energy, not a rate. Power is a rate, but it's energy in joules. So what we just showed here then is that the energy in is equal to the energy out. And or we can rewrite that in this nicely written form that F in D in is equal to F out D out. Energy in equals energy out. And this is the basic operation of a simple hydraulic press. And if energy in equals energy out, we are very happy about that, because that means conservation of energy. We are satisfying our Newton's laws. All is good with the world. We hope that we have conservation of energy. So if I were to summarize this, I would say that we can apply a force to one piston and get a force out of the other piston, no matter what the cylinder sizes were, because Pascal's law says that pressure is the same throughout, and the pressure is going to transfer that ability to do work from one piston to the other. It does that because even though the pistons are a different size, we can conserve energy in that they do travel the same volume. So a smaller piston would have to travel a larger distance than a large piston would have to travel to achieve the same volume of displaced oil. Therefore, the force times the displacement, a small force times a large displacement, is the same as a large force times a smaller displacement, and force times displacement is energy. So work in equals work out, energy in equals energy out. We have conserved energy, and we have been able to observe a system that is probably pretty useful. We can go back and we can, one last thing, relate that to the hydraulic cylinder, which is a useful application. And we can say, we can definitely conclude that there would be, there's a different area on one side than there is on the other side. So there's more force on one side than there is on the other side. And then we can draw conclusions about the distance one will travel versus the other one. And if we take that one step forward, we can say that it needs to conserve that volume over time. And when we're looking at the time element, that's when we get into the velocity. So if it has to travel that distance over a certain amount of time to conserve momentum, if the conservation of the conservation of volume has to be the same on this side and on this side, then they're actually going to have to travel at different speeds time t, they're going to have to travel at a different rate of displacement, which is speed. So when you're extending this cylinder and retracting it, they're actually going to act at a different speed. So that would be an application of this conservation of energy.